Я расшарю свой экран. Хорошо. Давайте сначала с кем не знакомы познакомимся. Меня зовут Алексей Устинов. Значит, у вас 5-й курс, ребята. Кто-то из вас слушал, наверное, лекции, возможно, по сверхпроводимости, которые я читал в весеннем семестре для 4-го курса. Откликнитесь, пожалуйста, кто-то слышал или нет. Для меня это важно знать, чтобы понимать, насколько серьезно потребуется введение во второй части моих лекций этого курса.
Да, слушаю.
А сколько примерно, ребят, вот будет, не знаю, сколько всего будет примерно, и сколько слышали курс? Ориентировочно можете мне сказать?
Может, чуть больше половины слушаю.
Чуть больше половины – это с физтеха, да? А вот меньше половины в чате.
Да.
Понятно. Здесь участвуют еще студенты МИСИС. Сколько примерно студентов МИСИС планируют участвовать в этом курсе?
Нас всего, получается, 16 или 17 человек. То есть я не знаю про своих одногруппников, слушали ли они курс лекций. Но вот половина из этих 17 людей точно не слушала.
Ну, хорошо, ладно. Значит, тогда все равно я оставлю какое-то впечатление по сверхпроводимости термина курса. Это будет примерно через пару недель. Хорошо, давайте займемся нашей сегодняшней работой. Значит, у нас сегодня 2 пары. Я написал Насте вопрос, на каком языке читать лекции. Вот. И, может, вы мне, поможете в этом? Год назад я читал этот курс по-английски. Это была такая просьба, или, скажем так, переводчик. У вас есть ли какая-то программа обязательного чтения вот этого курса по-английски? Кто-то знает, навестись?
Все курсы нам стараются читать по-английски.
Все курсы стараются читать по-английски. Хорошо. Тогда, наверное, попробуем по-английски. Значит, по крайней мере, я думаю, что сегодня мы начнем по-английски. Но дальше, если все-таки будут какие-то сильные пожелания и согласие организаторов, я готов перейти на русский. Вот. Ладно. So let's switch to English. My name is Alexey Ustinov, as I said. I'm professor of experimental physics in Germany, in Karlsruhe Institute of Technology, where I'm actually now. And simultaneously, I'm also leading a group at Russian Quantum Center and also teaching some courses at FISTECH and MISIS. Now, the topic of the course is solid-state quantum computing, which means that we are going to talk about solid-state technologies, semiconductor, superconductor technologies, which are possible to realize quantum computers. We'll move this right here. So this picture is just to entertain you. Let me go to the plan of the course. So we will start today with a basic introduction into quantum computing. And then I'm going to spend the second lecture of today introducing to you atoms and ions. And then we'll also talk a little bit about other types of qubits, which are not solid state, not condensed matter. These are photons, which we'll address in 1 week. Then we'll switch over to semiconductor devices and talk about quantum dots, talk about impurity spins in semiconductors. So basically using impurities as for encoding quantum information. And then the last part of this introductory qubits in solid state will be nitrogen vacancy and V centers. Also talk a little bit about fullerenes and electrons on surface of liquid helium. So this is a kind of superficial and introductory part, because really quantum computing until now was not demonstrated using these platforms. I'm talking about condensed matter qubits, which are bullets like third and fourth. Therefore, when talking about solid state qubits, we'll nearly completely focus on superconducting qubits, where quantum circuits, quantum processors have been already demonstrated in many places around the world, also in Russia. And we'll talk about various types of superconducting qubits. I'll give you the introduction into superconductivity in Josephson junctions, which will be, for some of you, a repetition of a fraction of my lectures on superconductivity, which took place this spring. Then we'll switch over to charge qubits and transmon qubits. Transmon is the working horse of majority of superconducting quantum processors nowadays. But then also talk about not only the existing technology, but talk more about more interesting physics and future. And here, devices as fluxonium, so special type of flux qubit, and also elements like superinductance come into play. Now, the superconducting qubits are very non-ideal nowadays, because they suffer from a variety of problems. And the major problem is their limited coherence. So we'll talk about, one lecture we'll spend on working on the coherence and discussing the microscopic mechanisms which limit the long lifetime of superconducting qubits and limit their error rate. And then in the last part of the course, we really go to a bit more advanced topics concerning the various ways of reading out superconducting qubits, talk about their manipulation, about the errors, their origin, and the ways to avoid errors, the ways to handle errors, so-called quantum error correction schemes. And also open a few topics concerning quantum simulation, which is not necessarily universal quantum computing, but it's more broad topic associated with understanding the quantum mechanics. And we will have also a lab tour, which I would be happy to do for you at my lab at MISIS in Moscow. When to do it exactly, we should probably discuss. I'm not sure I can be physically present for the tour, but I plan currently to be physically present for at least 2 double lectures. So we'll have the lecture of today and next week online. And then on September 15, there will be no lecture, because unfortunately at this time I will be flying to Moscow. And then there will be 2 lectures on November 22 and November 29, where I hope to see you all in person at Skoltech. And then we'll continue with the last few lectures online. So the exam for the course will take place most probably in the beginning of January. Still the date needs to be discussed with Nastya Andreyanova, so she will talk to you and find appropriate day which will overlap also at convenience with my schedule. That's the plan for the moment. So any questions concerning the organizational part from your side? I do not monitor. Somehow I do not see the chat here, but the chat is empty. Okay, I see the chat. All right, if you have any questions, please put them in chat. And if I don't see it immediately, I will check it before closing the lecture or before the break. But you're also welcome to interrupt me and ask a question directly if you want. All right. So this is a slide which I show in a similar lectures in Germany. So this AG stands for Arbeitsgruppe in German. So this is my lab, but topics which we work on in Moscow and in Karlsruhe are not, of course, identical, but they have a certain overlap and some interaction. So in Moscow, mostly we work with simple circuits demonstrating gates and demonstrating simple quantum processors. But there is also wider topic range opening up in different projects. In my lab in Germany, I work on devices using superconducting quantum circuits for quantum computing, for quantum simulations. We have pioneered the field of quantum metamaterials, starting from the first quantum metamaterial realized in our lab in 2000. The lab is most well known in the international community for our works on two-level defects. And that's what you see here on the right. You see my pointer now, so this is what you see on the right. This is the spectra of multiple microscopic defects coupled to superconducting quantum circuit. We'll have a lecture about that in our course. We also work on hybrid quantum systems, combining different type of quantum properties from different platforms, and also work on the technique which is called laser scanning technology. Now, the superconducting quantum circuits, they require fabrication. They require nano and micro fabrication using tools conventional in semiconductor electronics. That means we need clean room, we need evaporators to make thin films of superconductors. We need high vacuum to be able to control the pressure of oxygen, which we use to form tunnel barriers on superconducting circuits. And all that is available in my lab. It's in a clean room in Karlsruhe. At MISIS and in collaboration with Quantum Center, we are closely working on developing, setting up the clean room fabrication facilities. There is a new clean room recently finished at MISIS, and many opportunities to do practical work if you would be interested. For superconducting circuits, this could be also an opportunity. We also closely collaborate in Moscow with a group of Oleg Astafyev, the laboratory which is in Laboratorny Korpus and Fistech. At the basement, Oleg has been setting up this lab and over several years, and this has been very successfully working. So his group and my group closely interact also in the programs and projects related to superconducting quantum physics in Russia. All right, so this is just for you to have an idea from which corner I'm coming from. I also can tell that I graduated from Fistech in 1984, and then did my PhD in Chernogolovka, and then went to work around 1989 to work in the lab in Germany. And then since then, I've been changing a few places before I landed as professor in Germany in 1996. Changed to different universities, and over the last 14 years, I am at the University of Karlsruhe, which is now called Karlsruhe Institute of Technology. That's enough for the introduction, I think. Let's start with the course. Now, what are the requirements? I trust, of course, that Fistech students, they completely fulfill the requirements. You know quantum mechanics already, and you also have heard solid-state physics. Some of you have heard also my introduction into superconductivity, which was the spring semester, this spring semester. Now, requirements for the students from MISIS are the same. However, I'm not sure that all of you have heard of this. I mean, maybe some fraction of that you have heard, but you may need to make some reading to be able to really kind of fully appreciate the contents of the course. So these are requirements which actually are strongly recommended. for you to follow the course. And if you have some gaps there, please catch up. Quantum mechanics we need in the basis of foundation of quantum mechanics 1, non-relativistic quantum mechanics, including stationary Schrödinger equation, time-dependent Schrödinger equation, the spin dynamics, two-level systems, and this kind of things. Concerning the literature, there are some upcoming books in the world, which of course will be also available online, but there is no systematic curriculum to study quantum computing and solid-state quantum computing in particular in kind of same way as you study other fields like conventional courses of physics. So there is a kind of well-known, one can even call it the Bible of quantum computing, which is a book of Nielsen and Chuang, which is Quantum Computation and Quantum Information. It's not really discussing different platforms. And for example, superconducting quantum computing at the time of writing a book in around year 2000 indeed exists. So it was just made in 1999. Alex Zagoskin, who is a professor at University of Loughborough in United Kingdom, wrote a book which is called Quantum Engineering, which partially reflects the state of the field that time back roughly 10 years ago. But most of the information you can catch from lectures which are available online from different sources. And I recommend several review papers, which I will also put in the shared folder, which you can take and read in it. And some of them are written in a very introductory way. Some of them are in an advanced way. This is the introductory paper, which is actually called Quantum Engineer Guide to Quantum Superconducting Qubits, written by a team from MIT, led by William Oliver. Actually, the field is not just physics anymore. So to be able to understand and appreciate and handle quantum computing, you need to have knowledge not only in physics, but also in the subjects which are gathered under the umbrella of quantum engineering. Quantum engineering is a combination of knowledge in physics, in electromagnetics, electrical engineering, circuits, higher frequencies, technology, also in programming, to some extent in algorithms and so forth. So this combination of mathematics, physics, engineering, material science, that's something which is called quantum engineering. So quantum engineering program is something new, which actually for the first time in Russia we are setting up now in MSIS. So there is a kind of new study direction, which will start in the next year. We plan, this we will call quantum engineering, but for you as physicists, most of you are physicists, this will be, of course, kind of call to get extra education in some fields which you not normally know about. For example, microwave engineering, understanding how electromagnetic waves propagate, how they can be handled, what means impedance matching, and so forth. So this kind of things which are being taught by professors at engineering schools, but not necessarily for physicists. And this is required in this field to be able to follow. So as I said, I will put some of those review papers in the shared folder. I can recommend you this review, which is written, this kind of overview, Quantum Computing Progress and Prospects, which is a paper written by many authors, and it reflects the state of the field back 3 years ago, and also discuss different platforms. It's a very kind of descriptive story, but it gives you an overview which platforms of performing quantum computing have what are their advantages and disadvantages, what are their handicaps and priorities. And that's a kind of interesting to read. There is a similar paper which I will also put on archive on this shared folder, which has been written by Alex Fedorov, Alex Lvovsky, and Sergei Belousov. This paper, which is more written for kind of technology investors and businessmen who are interested into the field. So it doesn't contain much physics, but contains a lot of discussion concerning the advantages and disadvantages of different approaches. So that's something which is similar to this kind of quantum computing progress and prospects overview of the National Academy in the US. So look into this folder, you'll find some interesting reading there. Actually, I wrote to Nastya this morning to provide me a link, but she didn't. She will surely do it and also share with you in the next days. Any questions to the literature? Any requests, comments? Okay, not the case. Then let's start with introduction. There are many materials you could read on the internet about quantum computing. If you just Google quantum computing, you will get a lot of information, which was not the case only 20 years ago. It's really a rapidly developing field. And the field changed completely, and it became much more engineering than only physics around 2014, when actually Google hired a whole group of university professor Joe Martinez from the University of California in Santa Barbara to work on their project to build a quantum computer. About simultaneously, maybe 1 or 2 years earlier, a similar effort was started by company IBM, which first came up with a very simple, technically useless, but very interesting for demonstration, 5-qubit processor. And then they scaled it up to 16-qubit processor, and then 20, and then 50, and nowadays they offer over 100 qubits for their customers, and they have quite a few customers also. For example, Fraunhofer Institute in Germany bought an IBM quantum computer, and they're trying to do something useful with it. Of course, the usefulness of quantum computing at this stage of development of technology is very limited. So for commercial applications, may be useless even, but what is very encouraging is that you could really attack problems which cannot be addressed at all by classical computers. And this has been demonstrated in a seminal experiment performed by Google team in 2019, where they for the first time demonstrated so-called quantum supremacy or quantum advantage. So they were able to make a circuit which performed quantum we call it simulation, a quantum computation of a problem which is not treatable at all on classical computer. And the claim that time was that what they did in 20 seconds on this processor was requiring 10,000 years on the classical computer, on the best supercomputer in the world. Well, the specialists from the company IBM, who were competitors to Google and remain competitors to Google nowadays, they corrected them that, well, do it properly on a supercomputer will require much less time, only 2.5 days, but nevertheless, 200 seconds and 2.5 days is a large difference. So I think now, 3 years after, we can say that this experiment really demonstrates quantum advantage. However, the computation which was made there was completely useless. So there was nothing practical in that. So only the fact that the problem, which was compared with classical simulation, could not be solved on the classical computer. This was only claim which was maybe interesting for demonstrating the limits of this approach, demonstrating the validity of the approach. But the only application which the authors can think about excuse me, can think about that time was a random number generation, which is of course not much. So we'll talk about this a bit later, because we in the major part of this course will discuss superconducting quantum circuits, and you see here the head of Google touching the inner part of the refrigerator, which is the large cryostat with temperatures. When the whole thing is closed, it goes from room temperature above to about 4 Kelvin here, to 1 Kelvin here, and then down to about 20 millikelvin at the lowest temperature stage. And this whole computer is located at very low temperatures. Why? That's something we are going to discuss later on in this course. If you Google quantum computing, often you come across with a company which is called D-Wave, which builds the so-called D-Wave quantum computers. Now, just to orient you a little bit, D-Wave is a company which was first offering commercial quantum computers, starting from roughly, I believe, 2007 or so. Actually, was funding my group for some time before that. Now, the device which they developed is not a universal quantum processor. It's not a processor which works with quantum gates, quantum algorithms. It's the so-called annealer device. So it's a device which is performing so-called quantum annealing, which means that it's a quantum simulation where a certain type of Hamiltonian will be modeled by manipulating currents sent through this circuit. But nowadays they have over 5,000 qubits, and they claim their commercial applications are on the way. Still, it's very limited number of users there, and I would say that majority of physicists whom I know around the world are not fully convinced that this device is quantum. It can be partially quantum, can be considered as partially quantum, but even the quantum advantage of using this simulator is still being debated. So it's not something we are going to talk about in the first place, but partially these devices were also based on principles which we are going to discuss in this lecture course. All right, so this is just for you to sort of give the to flash quickly what is the state of technology which is based on the physics which we are going to discuss in this course. Now let's start with the first lecture. So the first lecture is actually will be a broad introduction into quantum computing, something which you have already heard, I believe, in some of the previous lectures. Some of you may not have heard because the audience is a little bit mixed, as I understand here. So some of this is going to be a repetition, but you will hear my version of that. And it's not going to be a difficult lecture. I believe something which will come later is going to be a bit more advanced. All right. So first slide is really simple. Back 200 years ago, no one even thought of anything besides abacus, shooting. When I was a boy, I have not seen any other instruments in the shops around 1960 plus. It could be just this device counting the numbers. And for these numbers, this device what people were using for about 3,000 to 4,000 years. They were invented a very long time ago. But then what happened in this in the previous century was really amazing. Now we have computers and not just doing the calculation, but they're doing everything for us. And that's something which is really fascinating in the revolution. In other words, how computers came about. That's an interesting story because looking back into that, one can also sort of make a parallel what is the state of the art now of quantum computing, and what can be the future of quantum computing? What should we expect? And looking back into the normal computing, goes back into the beginning of the previous century, and first person to name is often Alan Turing. So Turing machine is the thing which you learn in the informatics, studying the basics of programming and so forth. And in 1936, he published his famous work on computable numbers with an application to Entscheidungsproblem. Alan Turing actually was a pioneer there, but he was, of course, only working on theory. And that time, the ideas which he put forward were difficult to realize. So that time there were, of course, mechanical switches, and that's something which people learned to use to switch between states 0 and 1. But about that time already, electrical applications were on the way. And one of the first applications was the switch which was controlled by external voltage or external current. This was a relay. Electric relays were around since the already First World War, of course. And one of the persons who really contributed immensely into development of the hardware was a German engineer, Konrad Zuse. He's less known outside Germany. In Germany, there are streets which are named after him. He has been also living for many years here. But he was actually the first one trying to realize something which was kind of built based on ideas suggested by Alan Turing. I think Zuse learned about these ideas on the way when he was already making his first computer. Actually, his first computer was decimal and not binary. And then he realized that decimal is too complicated, so one has to go back to some simple circuits which can be scaled up and to perform also decimal calculations. Now, his first computer, which was called Z1, was actually the first world programmable computer, which evolved into the Z2 and Z3, which was already using partially vacuum tubes. But all these devices, unfortunately, were destroyed completely because Zuse was living and doing his experiments in Berlin, and everything was destroyed under bombs in the Second World War. But then Zuse was not forgotten. Actually, he started a company which didn't really develop itself too far, but it was acquired by industrial companies and finally was acquired by Siemens. And much of his work actually and ideas were saved for technology. Now, key development actually in computing should be acknowledged to John Neumann. He formulated the operation principles of computers and actually named relevant parts for the computer. So he named that the computer should have a processing unit, should have input and output tools, should have memory, and all that actually was the basis of building modern computers. It's very interesting that actually John von Neumann, between many other things, you know that he was actually responsible for breaking Enigma, using Enigma, the code of Germans during the Second World War, which allowed actually Britons and Americans to hear all to get all the information concerning the military activity, in particular in the sea. He is also known, John von Neumann is also known for laying down the mathematics of quantum mechanics. So he has been working on the field which is basically introduced the concept of Hilbert space, not space itself, but he introduced the concept that a quantum system state is just a point in Hilbert space. And then he also used the matrix theory to describe the evolution of this point in the Hilbert space by applying matrices and introducing unitary matrices as a formalism for quantum mechanics. So quite an outstanding person. But back to the hardware, because our subject here is a hardware, so Zuse was really one of the key persons. And the ideas which he was working on were in parallel developed in the US, where the first powerful digital computer was built as early already as in 1946. And you see this computer called ENIAC operating in, I believe, in Pittsburgh in the US at that time. So it consisted of thousands of vacuum tubes, which were used as switchers between 0 and 1, so this was a binary computer. And I guess what was the main job of people who maintained this computer? They were actually replacing the failing parts. They were replacing the vacuum tubes which were defects, and they were going defect very frequently. So this computer was actually never working for a long time. It was just working for some time and then but has to restart the calculations because there were errors coming in because of broken vacuum tubes. But nevertheless, this computer was actually powerful enough to be able to do calculation of the ballistic tables. So these are tables for artillery and missiles. If one wants to calculate the trajectory, these are ballistic tables done. Were used for that time, and calculating those tables for new weapons was very time consuming. So this computer was able to do it much quicker than humans can do it manually. And then further application of this computer was actually using it for first weather forecasts and also for a variety of other simple problems. So computer wasn't really used for too long time. I think it was stopped being in use in the beginning of 50s. About that time, an important event came about and the first transistor appeared. And this was actually made first by these three gentlemen, Bardeen, Batten, and Shockley in Bell Labs, where they were able to show that this actually device can have some gain similarly to a vacuum tube and can be made in a compact way. Moreover, they already at that time understood that it can be scaled up in larger numbers because one can reduce the size of transistors by various techniques and then make many transistors on the same chip. And the development of that really led to what we know now. So now we have huge semiconductor chips with huge number of transistors, which are all devices switching between 0 and 1s, and this is the logic which we use until nowadays. And this development was reflected in this exponential plot, which was first suggested by the founder of Intel. This was Moore, who basically said that every 18 months, the number of transistors on chip will double and the frequency will double and so forth. Well, the frequency doesn't double anymore in every year and a half because the signals, they basically reach the speed of light. And just recharging the capacitors and capacitances associated with transistors on chip takes time, and therefore the frequency is stagnated already over more than a decade at the level of about 3 gigahertz. But still the number of transistors on chip continue the exponential scaling. A bit maybe slowed down, but the number of atoms in the modern transistor with 7 nanometer technology can be counted in thousands. So this really shows the limit that you will have only few electrons in this kind of devices. Already have few electrons in this kind of devices, and quantum limitations are impossible to avoid. But that's actually, I told you this story to have you to have an overview how primitive was the beginning of the computation back 100 years ago, or even less than 100 years ago. What were the ridiculous looking were the first computers, and how far they are today. So what we are having now with quantum computing is something which is probably the beginning of middle of 50s, maybe end of 50s now, because that's about the time when Americans started making first integrated circuits, putting more transistors on many transistors on one chip. And that's something what quantum computers can do now, do computations with a few tens of qubits. And this number is steadily growing, already entering the hundreds. So that's a process which will continue in technology of the future. And that's something which I think for your generation is very exciting and very intriguing to observe and to get involved in. It's really a technological revolution which is happening nowadays in modern technology, something which your knowledge of physics can be invaluable to contribute. Okay, let's move on. So now let's talk about quantum. As we all know, the whole world is quantum. And quantumness of transistors, of course, was understood already in the 50s. So band structure of solids based on quantum mechanics. However, individual quantum objects like atoms, like if you take one atom, it's a very interesting system because it's really ideal. You have all atoms in universe identical, and it's intriguing really to use this kind of hardware for doing the quantum some useful tasks, complete some useful tasks. And one of the useful tasks is calculation of the properties of materials, for example, where one has to translate the quantum mechanics into the classical language because computers which calculate material properties are classical. So one has to use some approximations to simplify quantum problems. And these are approximations, whatever, Hartree-Fock or some other approximations which are being used to calculate material properties. They require translation into classical and then applying these classical results back to quantum. And people thought about this for a long time already. In most of the literature, we'll find Richard Feynman, who of course was a famous physicist, and he was actually one who brought this question up to white majority, for white audience in physics. Is it possible to build computers so that you use the laws of quantum mechanics to compute? So just not translating to classical, but really do it all quantum. But besides him, there were other people thinking of that, and in particular, there was a Russian physicist, Manько, who actually, about the same time or a little earlier, was thinking along the same lines and published the papers about that. Anyway, so this idea is rather appealing, and that's why people started thinking of the hardware which can be used to encode information in the quantum. Atoms are obvious, and atoms can be, of course, exist in any material, but in any material they interact with other atoms. So to be able to talk, so to say, to an individual atom, one has to isolate this atom. And this can be done by placing an atom in vacuum, but one needs to make sure that the atom doesn't fall down or fly away or is not lost. So to do this, one can use so-called optical lattices, which we'll talk about briefly in the lecture, in the next lecture. There are, of course, also photons, which are massless particles which propagate very freely. The disadvantage of photons is associated with the advantage. They keep their quantum states for a long time, but they are not much interacting with the rest of the world. So to make photons in particular interact with one another is a very difficult task. And this interaction is very limited and can be only achieved with materials with a so-called Kerr effect. And one really requires some hybrid systems to use photons as quantum building blocks. Something we'll talk about on the second lecture of today are ions. You may have, of course, heard of this. I will give you some brief overview, a bit superficial, of ions technology, where charged atoms, basically atoms with one or more electrons stripped away. They can be also trapped in free space by using electromagnetic fields. But the most promising are approaches using solid state. And that's where a lot of things have been happening over the last decade. So there are approaches using semiconductors. We'll talk about them briefly. There is a recent progress achieved that, but so far most complex circuits are only 2 qubits, though with very high fidelity of gates, one has to admit, and there is a promise to move forward using the whole background of semiconductor technology which exists and is available. But the field which is very interesting and very unique in a sense, and very which made very quick progress is the superconducting quantum computer, which actually is the field of my research and the subject also of the most part of the lecture of this course. So these are different qubits which can be used. The list can continue. There are many candidates which people propose and proposed before and keep proposing now. But the number, of course, is not exhausted yet, and there are many still interesting ideas to come. Now, why making quantum computers difficult? The problem is that to be able to do the quantum computation, you need to control something which is quantum and which is very gentle. So if you take an atom and you put an atom in electromagnetic fields or other fields, even gravitational fields, the state of atom is changing. And if you know how the state of atom is changing, you can take this into account. And actually what you do to quantum compute, you change the state of atomic-like systems. You change the quantum state by applying certain fields or forces to manipulate the quantum state. However, if this happens in uncontrolled way, something which you cannot follow, just to the interaction through environment with other atoms, other spins, and so forth, then this initial state information is lost, and your manipulation will not give the result you want to achieve with the same fidelity. So these uncontrolled effects which occur from the environment, they're called the coherence, and they limit the so-called memory or lifetime of quantum states, which means the lifetime, the time which you can over which you can reliably predict according to the laws of quantum mechanics, the state of a quantum system. And the coherence, it leads to errors. So the whole kind of agenda of building quantum computers is actually fighting with the coherence. It's not only the coherence, of course, that you need also to be able to do the manipulation. You need to read out the quantum information, and we'll talk about this later on today. But the coherence really is the biggest problem. And therefore, many proposals of building quantum computers, they were built based on the systems which can be made more or less coherent. And for some of them, it was not known how coherent they are. Like for superconductors, 25 years ago, it was impossible even to think that they can be quantum coherent in the sense of atoms. But trying by doing actually brought physics really far ahead. And now we know a lot more about coherence, also quantum mechanics, and also the ways to preserve the coherence. So let's start with a very basic slide. You may have seen it before. Actually, I see it all around. The slide I made maybe 15 years ago myself, but it now being present in many lectures of my colleagues around the world, just because probably it's very simple. The slide emphasizes the difference between classical bit of information and quantum bit of information. In a classical sense, in a classical computer, we encode information in 0 and 1s. And this can be level of voltage output of a transistor, 0 volt or 5 volts. But in principle, if you go back to the binary architecture of first computers, then you need just 2 states, and you need to be able to switch between those states. So you need a state 0, which can be location of a particle in one potential well on the left. And you could call, for example, the state 1 if the particle is located in the state 1 on the right well. And if you are able to switch between those states, and the states are not being mixed by errors, for example, there is no noiselet, or noise is very small, so there is no switching between 0 and 1, random switching uncontrolled. Then there's basically the hardware which you can use to operate a classical computer. Now, in quantum mechanics, things are different. If you make now a double-level potential, and you know this, or you should know from quantum mechanics 1, properties of spin 1/2 system. If you have spin particle with spin up and spin down, if you measure this particle, you either measure spin up or spin down, nothing in between. However, this particle is in superposition of the two states. And the superposition is described by potential, where at zero magnetic field, these two states, spin up and spin down, are possible with equal probability. However, due to the quantum nature of the system can be described as this double-well potential, where the states on the left well and right well are coupled by tunneling. Tunneling is a quantum mechanical process which, in principle, can be coherent. And the tunneling leads to the fact that the particle in the left and right well exists in the superposition of the left and right state. On the other hand, if one solves this problem using the Schrödinger equation and then diagonalize the problem, one gets the eigenfrequencies of the system, and it comes to the conclusion that the eigenfrequencies are associated with the two low-lying states, 0 and 1. And the states are stationary states, so if you prepare 0, it will stay forever. The state 1, in the absence of relaxation, also will stay forever. However, the wave function of the state 0 is this antisymmetric, so is this symmetric superposition of left and right, and the state 1, which is the first excited state, is the antisymmetric superposition of the left and right. So you are back now to this different basis of eigenstates of double-well potential. And of course, also there are higher states. There are states which are somewhere high up here, but we even don't discuss them because they are high up in energy. And if we use, for example, photons to couple states 0 and 1, for example, we can apply a photon to the system, and the photon will get absorbed and will go from state 0 to state 1. So we'll go from symmetric superposition to antisymmetric superposition. So this is the physics of spin 1/2 particle, which is described by this type of wave functions for the eigenstates. And any possible state of this two-level system, if we ignore the higher levels, we say that we don't have any processes which bring us so high up in inner energy, so that the only two states are important. Any state can be described as a superposition of 0 and 1. So we have this wave function psi is equal to alpha times 0 and beta times 1, where alpha and beta is the vector with complex coefficients, which describes the state of the two-level system. It's very convenient to present this state on the so-called Bloch sphere, which you should remember from quantum mechanics or from magnetic resonance classes, where actually we describe by Bloch sphere spin 1/2 particle and describe also manipulation about the spin 1/2 particle. So this applies to nuclear magnetic resonance, applies to electron spin resonance, which should be called paramagnetic resonance, discovered in Russia in Kazan. So basically, all those resonance techniques are describing spin particles state on a Bloch sphere. And here the upper state is often named as 0. We could call it North Pole of the Bloch sphere. The lower state is pure state 1. And then any superposition of those two states will occupy a point on this sphere with the radius of unity. And one can see that we have these two coefficients, alpha and beta. So they are complex numbers, but due to the fact that the sum of alpha square plus beta square is equal to 1, according to normalization, the allowed coefficients of alpha and beta are such that the points describing the states will be lying on the sphere. One can make a transformation in variables and go from alpha and beta to new variable, which will be theta and phi. and this will be a polar angle theta and azimuthal angle phi. And by then, basically, we describe the wave function now with these new coordinates as written here. So this will be this coefficient, real coefficient applied to state 0, and then this coefficient applied to state 1. So, of course, normalization also holds here. Now, it's interesting that the global phase here is not observable. So it's only when you fix the phase phi in the initial moment, you would be able to follow the change. So the variation of this angle, of this azimuthal angle, is the rotation around the equatorial plane of the Bloch sphere, and then rotations around x-axis or y-axis will be changing the projection on the z-axis. This will be then changing the probabilities of states, but not their phases, states of 0 and 1. So when we do the measurement of spin 1/2 system, as we know, as I already mentioned, you measure either spin up or spin down. So you either measure state 0 or state 1. Now we talk about different bases. Of course, at first I talked when measurements, I talked in the bases left and right. So either spin up or spin down. Now here we talk already in the basis which is in transformed variables where we have diagonal as the Hamiltonian. So these are eigenstates 0 and 1. So when talking about manipulation of qubits, you need always to think in which basis you describe the physics here, in which variables. And when you do the measurement, you either can measure direction of the spin, which will be left and right, or you measure in this picture if you are in the state, in the lower energy state, or in the high energy state. And this will be then basis 0 and 1. So these are different measurements. And typically, the measurement of a qubit in this kind of level of abstraction will distinguish between state 0 and 1. And again, if you do the measurement, you destroy the quantum state, you make a projection of the quantum state, and with certain probability you measure 0, and with certain probability you measure 1. If you have prepared the state 0, you will 100% of time measure the state 0. If you prepare pure state 1, you will 100% of time measure the state 1. However, if you prepare the state which will be on the equatorial plane, then of course the 50% probability you will measure the state 0, and 50% probability you will measure the state 1. And this kind of measurement actually collapses the wave function, and superposition is destroyed. So basically, you need to start the whole process of preparation of this state again, and then measure it again to gain the statistics. That's the usual process of quantum measurements, and this probabilistic nature means that you need to manipulate the qubit many times, 100 times, 10,000 times, and then measure the average outcome, average probability of one state or the other. There are also other types of measurements, so-called weak measurements, which we will not talk about in length, but there are also techniques where we, in this course, address this a little bit when one does the so-called measurements of quantum trajectories and so forth, where the quantum state is not completely destroyed, it's only partially changed during the measurement. All right. Then, as I mentioned, there are different bases. So one can measure in the basis of 0 and 1, but can also choose some other basis. For example, one can measure projection on the x-axis. One can measure projection on the y-axis. And then transformation of variables will be such that this will be the representation of this basis through 0 and 1s. This can be stated as basis plus, and this is basis minus. It's often used in literature as well. Or in particular, when we talk about rotation, we use Pauli matrices, sigma z, and so forth. One can also use the combined Pauli matrices, plus and minus. This is similar notation as here. Now, if you measure, for example, if you prepare the state which is like a pure basis state like this one, and the other state which is opposite to that, they're distinguishable in the basis of axis y, but they're indistinguishable in the basis 0 and 1. So one has to pay attention on that when choosing the basis, basically by when doing a quantum computation, one applies some preparatory pulses, like rotation by 90 degrees around certain axis, to be able to measure the state in desired basis. And this is something which we will talk about later on in examples when we talk about different systems. Okay, so this is things you certainly might have heard before concerning manipulation of spin 1/2 particle or two-level system on a Bloch sphere. Now let's talk about computing. When doing computing, in classical computing, we have the so-called gates, ventili. And these gates are basically simple things like you have operation NOT when you convert 0 to 1, or the same operation converts 1 to 0. There is also operation OR, which can give one output depending on the state of 2 bits, or operation AND, and so forth. Now, in classical computer, for example, these particular operations like OR and AND, they are not reversible. You have the output of 1 bit, and you cannot recover the initial information. So the information is lost. So classical computer is not reversible. Quantum computing is reversible computing. And it's kind of particular case of quantum computing, of reversible computing, which is also existing classically. At least the ideas exist how to implement this reversible computing classically. And this computing is also based on gates. So to say very simple, quantum gates are rotations on the Bloch sphere. The Bloch sphere describes two-dimensional Hilbert space. There are 2 dimensions here because you require only 2 coordinates on Bloch sphere, phi and theta, azimuthal and polar angle. In the case of single two-level system, you have this two-dimensional space, and then you basically rotate this state of the system, rotate the Bloch vector on the Bloch sphere over around different axes. And one of the well-known example is the so-called Hadamard gate, which is described by this matrix of rotation of the vector. So you multiply basically the initial vector of your state, alpha and beta, by this matrix, and you get a new state of the system. And intuitively, it's shown here what it does to states like state 0, initial state with the on the north pole. It rotates to the horizontal axis along x axis, and then if you have the state 1, then the same operation applied will rotate the state also to the equatorial plane on the opposite side. So basically, by applying the Hadamard gate, you can go from the basis state 0 and 1 to the basis state, which I introduced before, plus and minus. So this is just one example. But there are also other examples, many other examples of how you can rotate. In principle, there is an infinitely large number of ways of rotating the point on the Bloch sphere. You can use a combination of different gates to come from one point of the Bloch sphere to the other point of the Bloch sphere. And this is just the formality, which kind of set of gates you will choose for your quantum manipulation. So there is a NOT gate, which basically brings the point from one end of the Bloch sphere to the other. For example, if you have the state 0, it will get the state 1. But if you had the state in this point of the Bloch sphere along the x-axis, state plus, you'll get to the state minus. So it's kind of universal gate which rotates the vector on the Bloch sphere. When doing this gate, this NOT gate is often called a pi pulse. Why, I will explain to you in a moment. There is a Hadamard gate, which I just introduced, which is rotation by pi over 2, but this rotation can also happen along other axes. So there are also other types of rotations, which are all described by the pi over 2 pulses, and then depending on the initial phase, there will be rotation on particular axis. And there is an arbitrary rotation, which is called the phase gate. And this is interesting. For example, if one has a double potential and for a short time makes this potential asymmetric, slightly asymmetric, this changes the energy level separation. And if you go back to quantum mechanics and look what happens with the quantum system, if the energy level separation between two eigenstates is changed, it actually means that the state of this two-level system, basically the state described by alpha and beta, acquires a phase which is proportional to the variation of energy divided by Planck's constant times the time. So this is a factor in the exponent which comes into the which is identical to the phase, and basically this means that by applying this little z field for the spin 1/2 system, one does not change the population of the two states, 0 and 1. The states themselves slightly change in the energy. But what changes is the azimuthal angle phi. So you'll have a rotation over the azimuthal angle. And if you prepared the state in the equatorial plane, like for example here, this will mean just rotation along the equatorial plane. And then depending on the time which you wait, you will have a different phase accumulation. Here you'll have different phase gate. So this is basically a rotation around z-axis of the Bloch sphere. So all these are single qubit gates which can be implemented in conventional magnetic resonance technique as nuclear magnetic resonance or electronic paramagnetic resonance. Now, to do the quantum computation, having just single qubit gates is not enough, and that's something we'll talk about in a moment. Now, Pauli matrices describe particular gates. Actually, these are particular single qubit gates. They are often in quantum algorithms described by these circuit symbols. So this is like applying to the qubit sigma x rotation, this applying sigma y rotation, this applying z rotation. And if one has the magnetic field which one applies to a spin 1/2 system, one can introduce into Schrödinger equation, of course, stationary Schrödinger equation, this kind of potential which is introduced by field. And this basically described then by this matrix, this Hamiltonian, which can be split into the representation of the sigma x, sigma y, sigma z operators. It's quite often that sigma x, sigma y, sigma z being used to describe quantum states of qubits. So it's good idea to repeat this for your knowledge if you prepare yourself for next lectures of this course. And one of the suggestions, easy to read, is Feynman lectures of physics. For example, corresponding chapters 10 and 11 of volume 3. I think in Russian edition, it's volume 8 at the very end. It's ammoniac molecule. All right. Now, how to do this gates in reality? Well, the technique which is standard for the two-level system, which has two levels separated by certain energy difference, is the so-called Rabi rotation. Rabi oscillations are named after Isaac Rabi, got his Nobel Prize many years ago. And basically, he understood this very important phenomenon of atomic physics, that if you have two states and then you drive the system at the frequency of the transition between the two levels, so basically you have the energy difference between the two levels, you divide this energy difference by Planck's constant, you get the frequency, basically you get the energy of a photon, which you need to come from one state to another. But now you drive with classical field. You drive quite strongly. This could be electric field, for example, or magnetic field, just electromagnetic field as well, applied to atom. Then the system will coherently evolve between the two states. So if you prepare initially your system in the state 0, it will coherently go to the state 1 and then back to state 0 and state 1 and state 0. This is under assumption that this field which you apply is fully classical. So it's not really quantum description of that. And then depending on the amplitude of this field, you'll have then occupation of the excited state, which is on this plot is probability 1, and this on the state 0 is the lowest 0 here. Then you will have this rotation around the, for example, x-axis, and then this probability of finding the system with the state 1 will oscillate. Now, you see the frequency of Rabi oscillations. This is now the duration of the pulse of which you apply this driving field. If you change the amplitude of this pulse, then the rotation frequency increases proportional to the square root of the power, which means proportional to the amplitude of the drive. So if you choose particular amplitude, then you could say that you need just this time of the pulse to bring your system from ground state to the excited state. And this will be the pi rotation, or as we discussed already, this will be not gate. If you drive just half of that time, this will be pi over 2 rotation. This is when you apply these pulses to zero state, but you can apply these pulses to any state. In this case, this will be just rotation according to around the corresponding axis over this certain angle, either pi angle or pi over 2 angle. And this is a standard technique of preparing the states in NMR, and also standard technique at the same time. Same thing for preparing states in quantum bits, in qubits. Now, for doing quantum computing, 1 qubit is not enough. Of course, you have immense resource of information. You don't have anymore 2 states. You have an infinitely large number of states in your 2-dimensional Hilbert space on the Bloch sphere. However, to be able to do quantum computing, and this has been proved by people who made theoretical foundations for that, you need at least you need more than 1 qubit, of course. And besides single qubit gates, you need at least 1 2-qubit operation available, which means that you should be able to do this. And if you describe multi-qubit states, let's start very simply from 2 qubits. Suppose you have now 2 spins which interact with each other, just magnetically. Then we know that there are now, instead of just 2 states, there are more than 2 states. There are 4 states. Namely, one can choose those eigenstates as both spins up, left spin up, right spin down, left spin down, right spin up, and then both spins down. These are states 0, 0, 0, 1, 1, 0, and 1, 1. And then general 2-qubit states can be described now by the wave function, which is a superposition of those 4 eigenstates with corresponding coefficients, complex coefficients alpha 1, alpha 2, alpha 0, 1, 2, and 3. And now the Hilbert space is not 2-dimensional anymore, it's 4-dimensional, because we have 4 dimensions, we have 4 eigenstates and corresponding 2 coordinates for each states. And in general, n-qubit state, if you take n qubits, not just 2, will be a superposition of the 2 in the power n states. So for only 50 qubits, 15 states. And that's really something amazing. So it's an amazing resource of complexity and opportunity to encode the information. So if you have a memory which consists of quantum bits, to increase the memory by factor of 2, you don't need to increase the number of quantum bits by factor of 2. You only add 1 extra bit to n qubits, and then the Hilbert space is increased by additional 2 dimensions. So basically, this is really amazing resource of information storage and manipulation. Now let's go back to something which was the subject of Nobel Prize this year, to entangled states. If you take 2-qubit states, then you can naively think first that you multiply single qubit states and then you get all you need. But that's not the case. These so-called product states are a tiny fraction of the 2-qubit states. Most of qubit states are the so-called entangled states, states which you cannot really represent as a product of individual states of qubits. And one example which is well known is the so-called belt states. And in the basis of 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, let's think of a state which we can assign. We can, in principle, think that we can prepare this state for this 2-qubit state of the previous slide. So we can take basically this state, and we take this state, and then we prepare this with equal weight and with real coefficient here. This is the so-called belt state. Now, this state is a little strange. Strange in a way that it doesn't contain any eigenstate here. There is zero probability of measuring one qubit in state 0 and the other qubit in state 1. You can either measure both in state 0 or you measure both in state 1. And for this particular state, this will be with probability 1/2 for each of those states. That means that if you measured only part of that system, if you measured only one qubit, but you know that you had this Bell state, unavoidably, the other qubit is going to be in the state, in the same state as the first qubit you measured. And if you measure the state 1, the other qubit will be also in the state 1. And if you separate those qubits, you make them interact, and you separate them far away, then this should remain valid. And that's something which is actually in the basis of quantum teleportation, that by measuring one part of the coupled quantum system, entangled quantum system, you will know the quantum state of another. And by doing this, you will sort of instantly transfer the information over any distance, not thinking of the speed of light. But that's not something we are going to talk about in this course. We basically now talk about qubits here. Now, another entangled state is the so-called EPR. Don't mix it with electron paramagnetic resonance. It's Einstein-Podolsky-Rosen state, which is well-known state for which Einstein-Podolsky paradox was discussed in the 30s by Einstein and his co-authors, where a similar type of correlation between quantum states was discussed. And most celebrated example of that is the so-called Schrödinger cat, which of course you all heard about, that superposition of macroscopic states of many, many bits. And if you prepare them in such that one combination of bits is corresponding to living cat and the other one is corresponding to dead cat, then basically you can prepare the cat in superposition of life and death. And you know the example which was discussed, this was a decay of radium atom with certain probability that would kill the cat in the case of decay, but will not kill the cat in the case of no decay. Now, just a side comment, there is a whole field of physics actually, which is hunting for cats, building bigger and bigger superposition states of many, many bits. And the size here is not a physical size. The size is actually the number of elementary bits, or if you want, the size of the Hilbert space, where really superposition of many particles, so many quantum objects can be constructed and then observed, and their coherence can be studied. That's actually very interesting, how large can be a quantum system until the superposition is broken. And previously, people thought of this very naively, that, for example, a superconductor is a quantum state. All the electrons are in the same state at zero temperature. However, this is not described by individual wave functions of the electrons. It's described by the phase of the whole condensate. And therefore, the macroscopicity of many electrons in the superconductor is not just the size of the cat. So the size of the cat is really the number of elementary quantum states which you bring into interaction and superposition, and then study the coherence between different distant points in the Hilbert space. All right, let's move on. Examples of two-qubit gates there are many, of course, but one of the very well-known examples is the so-called knot. This is the conditional knot which one applies to qubits. And one qubit is being named here as control qubit, and the other is being named as a target qubit. And then, depending on the state of the control qubit, target qubit can flip or not flip the state. So if you apply this matrix to this four-dimensional state, then the states 0, 0 and 0, 1 will not change after applying the state, but state 1, 0 will change to 1, 1, because you have to swap the state of the target qubit if the control qubit is in 1, and the state of 1, 1 will change to 1, 0. So as I said, a universal quantum computer can work on the condition that you have at your disposal some single qubit gates. There are many, as I told already, and at least one 2-qubit gate. Either this one or some other, but you need at least one 2-qubit gate, or more than 2-qubit gates at your disposal. Then you can really do quantum computing. And that slide is about generation of the entanglement. So it's sort of something which people not always note, at least don't pay attention, but it's very interesting. So once you have created an entangled state, for example, you created a Bell state, like 0, 0 plus 1, 1. And then you apply just a single qubit operation to qubits which have been interacting and then not interacting again. By changing the state of one qubit, you change the other qubit simultaneously, because you change the quantum state of the entangled system. So you cannot go out of the entanglement so easily. There is a procedure of doing the disentanglement, but that really requires quite sophisticated technique. Typically, you need to reverse operations in time. So in this case, you will sort of make the entanglement back by applying same type of inverse rotations. So by measuring the state of only one qubit in the entangled qubit register, you will be able to determine the states of other qubits, because you really project a fraction of the Hilbert space of the coupled system. And that's really something which Einstein called spukhafte Fernwirkung, spooky action at distance, which really brought him very uncomfortable thoughts, which he was sharing a lot, as you probably read about with Bohr and so forth, about quantum mechanics. But that's more like interesting philosophy of quantum mechanics, which is still being debated and requires human experience beyond daily things to be accepted and brought into our intuition. Now, if you have a classical computer, then, as I said, you have classical gates, which are often non-reversible, because you get 2 bits of information and then you get 1 at the output. And in this case, you run the algorithm with one or more, with some input bits, and you get some output bits. In the quantum computer, the number of input and output bits is the same, which is not necessarily the case for the classical computer. And you get basically, you manipulate the qubits with those rotations, also rotations in the multidimensional Hilbert space, and then you get some output. And then as a result of computation, you basically need to determine this final state, which will be the state transformed from the initial state. So you have multidimensional Hilbert space, then you go from point A to point B in this multidimensional Hilbert space. And that's that point B, which you measure, is a result of your computation. And quantum algorithms have been proposed by different people. You may have heard of those names. One known algorithm is so-called Deutsch-Jozsa, where you decide whether the coin is faked or real. So classically, you need to look at the coin from one side and from another. Fake coin will have, for example, eagle on both sides, and real will have it's not only one side. So you need to do it twice for the coin, but for the quantum algorithms, you can do it by one measurement or one step. There is also search algorithm, Grover's algorithm, and also well-celebrated Shor's algorithm for factoring large numbers, prime numbers, which are the basis of a RSA protocol used for conventional, for modern cryptography. Well, this is something which was motivating the development of quantum computers. Now, those algorithms, all of them have been implemented in real quantum computers. In simple terms, for example, Shor algorithm was implemented to factor numbers like 15 or 20, 20 plus. But practical, of course, applications where these algorithms will become important are still on the way and not have been achieved so far. So the idea of quantum computing, as I said, you start some initial state of your multi-qubit register, then you execute algorithms by applying single and multi-qubit gates, and then you read out the result. And this all needs to be done in a time which is still short enough compared to the coherence time. So you should have your quantum memory not fully broken. So if you wait too long, then the coherence will create errors and the result will be not precise. But it's interesting that if you get the precision, not 100%, but even 80% for many of the computations, it's already very, very valuable. So it's something which many people, including myself, back some years ago, completely misunderstood, that actually quantum computer can be also good if it does approximate calculations. So if it calculates the result with only limited fidelity, not 100% fidelity. That's quite interesting. And this probably is my last or pre-last slide. Maybe I will stop here and start next lecture from this slide, just to have a break. Now, I need your help because I got no table of your courses. We are now 1.5 hours through, so it's 12 in Moscow now. What is your time for the break? Can you tell me, please? 50?
Да, в 11:50.
Ага, извините, что я затянул, просто я думал, что 1,5 часа ровно. Так, значит, потом перерыв какой у вас в 11:50?
В 12 начинается следующий класс.
Хорошо, давайте сейчас сделаем перерыв до 12:10. И следующую лекцию мы тогда сделаем сегодня покороче. У вас, как я понимаю, там еще сегодня что-то есть, поэтому я не должен затягивать, чтобы успеть вписаться. Хорошо, перерыв 10 минут.
Можно вопрос задать?
Да, пожалуйста.
А вы можете вернуться на страницу с RABI-осцилляциями,
Да, конечно.
пульсами и все вот это вот?
Да-да.
Вот, да, видимо, вот это. Ну, просто давайте временно забудем про сферу Блоха и рассмотрим атом, который может находиться либо в основном, либо в возбужденном состоянии.
Да.
Вот. Если мы используем резонансный импульс, то вероятность обнаружить атом в возбужденном состоянии будет равна квадрату синуса от длительности импульса. Вот. Получается, что π пополам пульс в такой нотации нам как бы гарантированно перекинет атом из основного состояния в возбужденное.
Да.
Вот. А согласно вот этой картинке складывается такое ощущение, что у нас перекидывает из основного состояния в возбужденное не π пополам пульс, а π пульс.
Так, давайте вернемся. Пи-пульс — это вращение на блоховской сфере, значит, переворот стрелки фактически, да. Но вы про блоховскую сферу не хотите смотреть, вы хотите понять это сейчас по вот этой вот картинке, да? И вы сделали утверждение, что у вас амплитуда состояния пропорциональна квадрату косинуса, да? Или синуса, извините. Я правильно вас понял?
Ну, да. Квадрата синуса.
Ну, это же как бы вот эта формула, она не содержит никакого вращения здесь. Это просто есть состояние на сфере Блоха. Для того, чтобы описывать вращение, вам необходимо решить задачу Раби. То есть вы должны...
Нет, вот я...
Да.
Я как раз таки вот говорю, что если честно расписывать Гамильтониан, Раби и так далее, получится, что вот вероятность обнаружить атом в возбужденном состоянии равна квадрату синуса от длительности импульса. Вот. То есть там вот нету как бы одной второй. Вот, поэтому пиполам импульс как бы гарантированно перекинет атом из основного состояния в возбужденный. А согласно вот такой вот нотации со сферой Блоха, пиполам импульс перекинет атом из основного как бы в состояние 50 на 50.
Ну, смотрите, значит, мы с вами говорим о Гамильтониане Раби, его нужно написать, так? Это как бы, вот на слайде здесь ничего этого не было. Значит, дальше, чтобы решить задачу Раби, вам необходимо перейти в вращающую систему отсчета. То есть вам нужно перейти в координаты, которые вращаются с частотой внешнего поля. Задача Раби получаете представление, эквивалентное блоховской сфере спин 1/2. То есть мы сейчас с вами говорим, в общем-то, о двух разных гамильтонианах. Одно дело, когда мы прикладываем переменное поле для двух состояний 0 и 1. А другое дело, когда мы уже в системе координат Раби, то есть в вращающей системе отсчета, рассматриваем ее как двухуровневую систему. Я думаю, что вот этот вот коэффициент, он там вылезет.
Окей.
Посмотрите описание вот задачи Раби и переход в rotating frame. Вот. И там это должно быть понятно. То есть там нужно пренебречь сразу медленно вращающимися членами, оставить только быстро вращающиеся. Точнее, пренебречь, извините, быстро вращающимися членами. Вот. И дальше вот в этой новой reference frame получится, значит, описание задачи Раби.
Окей.
Угу. Ладно, давайте я тоже немножко отключусь. Может, на секунду.
Можно задать вопрос?
Да?
Вот я этих часов увидел.
Угу.
Я бы хотел узнать, что именно вы хотели вот в курсе сверхпроводимости. У меня тоже просто был курс, но хотел бы узнать, насколько пересекать это.
Значит, по сверхпроводимости мы проходили, в принципе, введение по книжке Шмидта в основном. Вот. Если вы хотите прочитать, это будет полезно. Но я сделаю введение здесь. Как бы полезно, конечно, вам знать, что такое сверхпроводник и что такое эффект Джозефсона. Но я постараюсь все-таки, чтобы все остались на ходу, посвятить лекцию повторений. Объем моего курса – это книжка Шмидта. Ну, почему? Я рассказывал и БКШ, было 2 лекции, все теории БКШ, теории Гинзбург-Ландау. Рассказывал сверхпроводники первого-второго рода, и примерно там 3 лекции были про эффект Джозефсона и его приложение такой, даже одна лекция про кубиты была введение такая. Но это все будет в этом курсе.
Ну, вы кафедре на Московского ровно такой же.
Повторите, пожалуйста, вопрос.
Не, я говорю, что я по кафедре на Московского вот ровно такой же.
Ну, тогда вам этого хватит. А вам читал Иван Храпач или кто-то?
Нет, я нам читал Павловский Валерий.
Понятно. Ну, если вы это как бы уже слышали, я еще раз повторю какие-то ключевые понятия, и этого хватит нам.
Понятно.
Угу, конечно.